In order to be able to show the alternative representations of the system, so what we have done so far is to say that the governing equations are ODEs, then we show them by transfer functions in the frequency domain or state space representations, and we learned how to change the representations back and forth, and also learn to show the state space representation via phase variable such that we can draw the signal flow graphs based on them. Now we want to show this simple example, the equation of this simple example, as a review to go for alternative representations. We have 4 different alternative representations. This guy here, C dot signal here, is like the equation I want to write is minus AI multiplied by CI, so comes there, and also plus RI gives me the, let's say, CI dots. So in the Laplace transform, I can write SCI plus AICI is equal to RI. This means that CI over RI can be represented as 1 over S plus AI. So 1 over S plus AI can be represented as a signal flow graph that is a feedback system. Now, the first representation, alternative representation of the system via phase variable, we did this example for the phase variable representation. Now, if I want to do it cascade, we have the poles here. The poles means the roots of the denominator here. So the transfer function of this system can be shown as 24 multiplied by 1 over S plus 2 multiplied by 1 over S plus 3 multiplied by 1 over S plus 4. So in terms of block diagram, it's like I have the RS and it's multiplied by 24, then it's multiplied by 1 over S plus 2, then multiplied by 1 over S plus 3, then multiplied by 1 over S plus 4, and we will get CS. Clear? Now, each of these are 1 over S plus A. Clear, guys, that each of these blocks are 1 over S plus A? So
yes, sir.
Okay. I would be happy to hear from you guys. So, if I want to draw the signal flow graph, if I say that this part is x1, this signal is x2, and this is x3, x1 can be shown as 1 over S x dot 1 and minus 4. Then it's multiplied by, it's like 1 over S minus 3. This is x2, x dot 2. And then we have, these are 1, this is 1. And then we have this guy. X dot 3, x3, x dot 3, 1 over S minus 2, and this is 24, and this is 1 again here. So for each of these points, this signal here, the signal here and the signal here, I can write equations. What are those equations? I can write x dot 1 is minus 4x1 plus x2. X dot 2 is minus 3x2 plus x3. X dot 3 is minus 2x3 plus 24r. And y, which is c, is equal to x1. So this can be represented as minus 4, 1, 0, 0, minus 3, 1, 0, 0, minus 2, x plus 0, 0, 24, r, and y is 1, 0, 0, r. So you see that for this problem in the cascade form, I get this representation, while for the phase variable, I had this representation. So this was phase variable technique, where y was now versus cascade form. This is the cascade form. You see that A matrix changed to this guy. The A matrix is the system matrix, since it contains the terms relative to the internal system itself. The system matrix contains the system poles along the diagonal. You see that these guys are the poles of the system. Clear? Okay. In the second representation, we have parallel form. We want to show the system as parallel. How we do that? We say the transfer function with partial fraction expansion can be shown as 12 over s plus 2 minus 24 s plus 3 plus 12 s plus over s plus 4, which is c over r. So cs is like 12 over s plus 2 r s minus 24 over s plus 3 rs and plus 12 over s plus 4 rs. Clear how we wrote these things? So this is like k1, k2, k3, which is partial fraction expansion discussed in the lecture 2. Now if I say this is x1, this is x2, and this is x3, I can represent this system as C and R, and let's use different colors. X1 is like 12R minus 2, 1 over S, x1, this is x dot 1. X2 is like minus 24R minus 3 x2 x dot 2 1 over S. And if this is x3, minus 4 1 over S x3 x dot 3, and this is 1. So what are the equations here? X dot 1 is minus 2 x1 plus 12 r, so I'm writing for here. Then x dot 2 for this point, minus 3 x2 minus 24r. Then writing to this point, x dot 3 is minus 4x3 plus 12r. And for C, which is y output, we have 1, 1, 1, x, because we have x1, x1 plus x2 plus x3. So this can be shown as minus 2, minus 3, minus 4, 0, 0, 0, x plus 12 minus 24, 12, r, and y can be shown as 1, 1, 1, x. Clear? So this time you see that the A matrix became diagonal. The third representation, we have the phase variable, then cascade form and parallel form, and each of them have different representation. Any questions so far? The third representation is controller canonical form. If I have this equation, what is the phase variable? We discussed the phase variable for this is x dot is equal to 0, 1, 0, 0, 0, 1. Then we have minus 24, minus 26, minus 9, x plus 0, 0, 1, r, and y is like 2, 7, 1, x. This is the phase variable. In the control canonical form, what we do is like to change the, if we had like x dot 1, x dot 2, x dot 3 equal to let's put it here. The phase variable 0, 1, 0, 0, 0, 1, minus 24, minus 26, minus 9, x1, x2, x3, plus 0, 0, 1, r, and y is 2, 7, 1, x1, x2, x3. The thing is, we have to write this form and then change the names. Change names to x3, x2, x1. It's like making the vectors vice versa, and this is x3, this is x1. Then make the order from like x dot 1, x dot 2, x dot 3. Now, x dot 1 would be minus 9, minus 26, minus 24, x1, x2, x3, plus 1, 0, 0, r. So x dot 2 would be 1, 0, 0, and x dot 3 is 0, 1, 0. And y, the new y would be, if I change this to x3, x2, x1, would be 1, 7, 2, when we are writing it as x1, x2, x3. So in the controller canonical form, what we do is to show it as phase variable first, then change the order of the x variables from 1 to n to 1, and then represent them again from 1 to n. But this time, the matrices and the vectors will change their order for sure. So you see that phase variable form and controller canonical form contain the coefficient of the characteristic equation, yes, These are the coefficients of characteristic equation 24, 26, 9, the negative forms. The first one is in the top row here. So in the phase variable is in the lower row of the matrix. They're called companion matrices, okay? So if you want to represent it as signal flow graph, you will get the same system. You will get the same representation, just change of the names will happen. The final one is observer canonical form. In this form, the methodology is like this. You have the transfer function and you divide them by the largest power of s. That is, you multiply this by S3 and you multiply it by S3 because 3 is the largest power of present s's here. So you will get 1 over s plus 7 over s 2 plus 2 over S3, and this is like 1 plus 9 over S plus 26 over S2 plus 24 over S3, and this is like CS over RS. So what do we do is, like, if you multiply these guys, you will get CS plus 1 over S 9 CS plus 1 over S2 26 CS plus 1 over S3 24 CS plus equal to 1 over SR plus 7 over S2R plus 2 over S3R. Then if I reorder these as 1 over S R minus 9C plus 1 over S2 7R minus 26C plus 1 over S3 2R minus 24C. If we represent it like this and say that this is x1, x2, x3 again, let's see how we represent it. If I have C here and R here, okay. If I say this is x dot 1, so x dot 1 is like, if this is x1 and that is x dot 1, I will get x1 1 over s x dot 1, so integration of that. I have minus 9 from the C because it's connected, and x dot 1 plus R. The second part, if I use red color, I will have minus 26 from C x2 sorry, x dot 2, I was right, x dot 2, and this is x2, which is 1 over s, okay, and we have this 7 from the input, and finally we have x3 x dot 3, which is 1 over s. This is like, sorry, this is like from here we have minus 24c and we have 2r. It is like, yeah, 2 there. So this is the observer canonical representation, if I write the equations here for x dot 1, I write it here. I have minus 9x1 plus 1r. For this part, x dot 2 is minus 26x1 plus 7r, and x dot 3 is minus 24x1 plus 2r, and y is the output x1. So what do we get here? We get the matrix in this form. X dot is equal to minus 9, in the x1 we have, x dot 1 we have also these ones, I forgot x2, and here we have this 1 from x3. Okay, we have minus 1, 1, 0, minus 26, 0, 1, minus 24, 0, 0, x plus 172 r, and y is 100 x. If you compare it to controller form, this one was the controller form. Let me copy and paste here. This is controller form. This is observer form. What do we see? You see this guy has become transposed. This guy has transposed here, and this guy has transposed here. So if you have the controller form and you do A transpose, change the places of the B and C matrices and transpose them, you can change the observer form and controller forms to each other, and because of this they are called duals. Okay, clear? So this guy here is like transposed, this is transposed, but changes its place to here, and this guy comes here. Also C and D and C and B, and B and C are changing places, transpose, and A is just being transposed as the form. So it's like if you have the phase variable, then you can find the controller form. How do you do that? You have x1, x2, x3. You just change the order to x3, x2, x1 to get the controller form, and from controller form to get the observer form, you do A transpose, you get B by C transpose, and you get C by B transpose of the controller case. So please, for this example, obtain these forms like phase variable, parallel form, cascade form, controller form, and observer form. We have the answers here. Just make sure you can obtain them and draw these signal